The National Electrical Code requires each transformer enclosure to be grounded independently with its own ground rod. The ground rods should be placed as far apart as possible, at least 6 feet apart, to ensure independent grounding paths. The ground rods must be bonded together at the transformer enclosures. The bonding conductor should be at least 6 American wire gauge copper. It is also recommended to connect the equipment grounding conductors from the panels to the building beams. This provides an additional grounding path and helps to ensure a low resistance path to ground. You will need to use 2 ground rods, one for each transformer enclosure, and bond them together. You can then run a ground conductor from each panel to the building beams. For the 480/240 volts 3-phase delta/delta transformer, a dedicated ground rod is required. This ground rod provides a direct path to earth for fault currents, protecting equipment and personnel. Similarly, for the 480/208/120 volts 3-phase delta/Y transformer, a separate ground rod is also necessary. This ensures that each transformer has its own independent grounding system. The minimum separation distance between the ground rods is 6 feet. This separation helps to minimize the interaction between the grounding systems of the 2 transformers. Bonding the ground rods together is essential for creating a common ground potential. This bonding is achieved using a 6 American wire gauge copper conductor or larger. Connecting the equipment grounding conductors from the panels to the building beams offers an extra layer of protection. This connection to the building steel provides an additional low impedance path for ground fault currents. Grounding is a critical aspect of electrical safety and equipment protection. Ensuring proper grounding practices are followed is paramount for a safe and reliable electrical system. Always consult the latest edition of the National Electrical Code and local regulations for specific grounding requirements. The purpose of grounding is to provide a low impedance path for fault currents to return to the source, which facilitates the operation of overcurrent protective devices such as circuit breakers and fuses. This helps to minimize the risk of electrical shock and equipment damage. A properly grounded system also helps to reduce electrical noise and improve the overall performance of sensitive electronic equipment. The size of the grounding electrode conductor, which connects the transformer's neutral point to the ground rod, must be sized according to NEC Table 250.66. This table specifies the minimum size of the grounding electrode conductor based on the size of the transformer's secondary conductors. The grounding electrode conductor should be securely connected to the ground rod using an approved grounding clamp or connector. The ground rod itself should be at least 8 feet in length and should be driven into the ground until at least 8 feet of the rod is in contact with the soil. In areas with high soil resistivity, it may be necessary to install multiple ground rods connected in parallel to achieve the required grounding resistance. The resistance to ground of the grounding system should be verified using a ground resistance tester. The NEC recommends a maximum resistance to ground of 25 ohms for a single ground rod. If the resistance exceeds this value, additional ground rods should be installed. The connection between the equipment grounding conductors and the building beams should be made using approved grounding connectors. The building steel must be continuous and effectively grounded to provide a reliable grounding path. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Ground connections should be checked for tightness and corrosion. Ground rods should be inspected for damage and replaced if necessary. The grounding system should be tested periodically to verify its resistance to ground. Proper grounding is crucial for protecting electrical equipment and personnel from the hazards of electrical shock and fire. Adhering to the NEC and local regulations for grounding is essential for ensuring a safe and reliable electrical system. Remember that this information is for general guidance only, and it is always recommended to consult with a qualified electrician or electrical engineer for specific applications. They can assess the specific site conditions and design a grounding system that meets all applicable requirements. They can also perform the necessary testing and inspections to ensure that the grounding system is properly installed and functioning correctly. Grounding is not only a safety measure but also a key component of the overall electrical system performance. A well-designed and properly installed grounding system can improve the reliability and efficiency of electrical equipment, reduce electrical noise, and prevent damage from voltage surges and lightning strikes. In summary, proper grounding is essential for a safe, reliable, and efficient electrical system. Always follow the NEC and local regulations and consult with qualified professionals to ensure that your grounding system is properly designed, installed, and maintained. The installation of ground rods typically involves driving them into the earth to a specified depth. The depth and number of ground rods may vary based on soil conditions and local electrical codes. It is essential to consult with a qualified electrician or electrical engineer to determine the appropriate grounding configuration for a specific application. The connection of the grounding electrode conductor to the ground rod should be made using a listed and labeled connector suitable for direct burial. This connection should be protected from corrosion and mechanical damage. The equipment grounding conductor, which runs from the electrical panel to the building beams, should be sized in accordance with NEC Table 250.122. This table specifies the minimum size of the equipment grounding conductor based on the size of the overcurrent protective device protecting the circuit. The equipment grounding conductor should be connected to the building beams using a listed and labeled grounding connector. The building beams should be effectively bonded together to ensure a continuous grounding path. This bonding can be achieved by using bonding jumpers or other approved methods. The resistance of the grounding system should be tested using a ground resistance tester. This test measures the resistance between the grounding electrode and the earth. The NEC recommends a maximum resistance of 25 ohms for a single grounding electrode. If the resistance exceeds this value, additional grounding electrodes should be installed in parallel. Regular inspections and maintenance of the grounding system are essential to ensure its continued effectiveness. These inspections should include checking the condition of the ground rods, grounding connectors, and grounding conductors. Any damaged or corroded components should be replaced immediately. The grounding system should also be tested periodically to verify its resistance. Proper grounding is crucial for protecting electrical equipment and personnel from the hazards of electrical shock and fire. Adhering to the NEC and local regulations for grounding is essential for ensuring a safe and reliable electrical system. It is also important to note that the grounding requirements for transformers may vary depending on the type of transformer and the application. For example, the grounding requirements for a separately derived system, such as a transformer, are different from the grounding requirements for a service entrance. The NEC provides specific guidelines for grounding separately derived systems in Article 250.30. These guidelines include requirements for the size of the grounding electrode conductor, the location of the grounding electrode, and the bonding of the grounding system. It is essential to consult with a qualified electrician or electrical engineer to ensure that the grounding system for a transformer meets all applicable requirements. They can also provide guidance in the selection and installation of appropriate grounding equipment. Grounding is a complex topic with many different aspects. It is important to have a thorough understanding of the NEC and local regulations to ensure that electrical systems are properly grounded. A properly grounded electrical system is essential for the safety of people and equipment. Remember that the information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical engineer for specific applications. To further elaborate, the NEC mandates that each separately derived system, which includes transformers, have its own grounding electrode system. This requirement stems from the need to establish a dedicated low-impedance path for fault currents to return to the source. By having separate grounding systems for each transformer, the potential for circulating ground currents and voltage differences between different parts of the electrical system is minimized. The separation distance of at least 6 feet between ground rods is intended to reduce the interaction between their respective zones of influence. When ground rods are placed too close together, their effectiveness in dissipating fault currents can be diminished. Bonding the ground rods together with an O6 American wire gauge copper conductor or larger creates a common ground potential between the two transformers. This bonding helps to ensure that both transformers are at the same electrical potential, reducing the risk of voltage differences and potential shock hazards. The recommendation to connect the equipment grounding conductors from the panels to the building beams provides an additional grounding path, which can further enhance the safety and reliability of the electrical system. This connection to the building steel can help to reduce the impedance of the grounding path, allowing fault currents to flow more easily back to the source. In addition to the requirements for ground rods and bonding, the NEC also specifies requirements for the size and type of grounding electrode conductor. The grounding electrode conductor is a conductor that connects the transformer's neutral point to the grounding electrode. The size of the grounding electrode conductor must be based on the size of the transformer's secondary conductors, as specified in NEC Table 250.66. The grounding electrode conductor must be made of copper or other approved material and must be protected from physical damage. The grounding electrode must be a ground rod, ground plate, or other approved grounding electrode. The grounding electrode must be installed in accordance with the NEC and local regulations. The resistance to ground of the grounding electrode system must be measured using a ground resistance tester. The NEC recommends a maximum resistance to ground of 25 ohms for a single grounding electrode. If the resistance exceeds this value, additional grounding electrodes must be installed in parallel. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Ground connections must be checked for tightness and corrosion. Ground rods must be inspected for damage and replaced if necessary. The grounding system must be tested periodically to verify its resistance to ground. Proper grounding is crucial for protecting electrical equipment and personnel from the hazards of electrical shock and fire. Adhering to the NEC and local regulations for grounding is essential for ensuring a safe and reliable electrical system. Furthermore, when dealing with transformers, it's essential to understand the concept of impedance. Impedance is the total opposition to current flow in an alternating current circuit, and it includes both resistance and reactance. A low impedance grounding path is crucial for effectively clearing ground faults. When a ground fault occurs, a large amount of current flows through the grounding path. If the impedance of the grounding path is too high, the fault current may not be sufficient to trip the overcurrent protective device, such as a circuit breaker or fuse. This can result in a dangerous situation, as the equipment may remain energized and pose a shock hazard. By providing a low impedance grounding path, the fault current can quickly reach a level that will trip the overcurrent protective device, de-energizing the equipment and preventing a potential shock hazard. The size and type of grounding conductors, as well as the quality of the connections, all contribute to the overall impedance of the grounding path. Therefore, it's essential to use appropriately sized conductors and ensure that all connections are clean and tight. In addition to the grounding requirements for the transformers themselves, it's also important to consider the grounding requirements for the electrical panels that are fed by the transformers. The NEC requires that all electrical panels be grounded to a common grounding electrode system. This ensures that all parts of the electrical system are at the same electrical potential, reducing the risk of voltage differences and potential shock hazards. The equipment grounding conductors from the panel should be connected to the building beams, as previously mentioned, to provide an additional grounding path. The size of the equipment grounding conductors must be based on the size of the overcurrent protective devices protecting the circuits in the panels, as specified in NEC Table 250.122. The equipment grounding conductors must be made of copper or other approved material and must be protected from physical damage. The connections between the equipment grounding conductors and the building beams must be made using listed and labeled grounding connectors. The building beams must be effectively bonded together to ensure a continuous grounding path. The grounding system for the electrical panels must be inspected and tested regularly to ensure its continued effectiveness. Ground connections must be checked for tightness and corrosion. Ground conductors must be inspected for damage and replaced if necessary. The grounding system must be tested periodically to verify its resistance to ground. Proper grounding of electrical panels is essential for the safety of people and equipment. Adhering to the NEC and local regulations for grounding is essential for ensuring a safe and reliable electrical system. You must ground both transformers and you must bond them to each other. This means each must have their own ground rod, no closer than 6 feet from each other, and both rods connected to each other with at least number 6 copper wire, unspliced.